Welcome back to the deep dive. We know that if you're listening, you are probably operating at the absolute cutting edge of architecture design.
Which means you live in that world where every single tensor operation, every memory access, it all has real, tangible implications for scaling these foundational models.
And that's exactly why our mission today is so precision-guided. We're cutting straight to the core of this constant evolution in deep network architecture.
Right, the quest to scale beyond the residual connection paradigm that we all know. We're focusing entirely on one key piece of source material, the paper on Manifold-Constrained Hyper-Connections, or mHC.
Okay, so let's set the mission. We all know that modern deep learning, especially at this massive scale, it still hangs on that stable foundation built by ResNets.
That essential identity mapping.
Exactly. So the challenge, and what this paper lays out, is how do you evolve that topology, make it richer, without just completely sacrificing the stability that it gives you?
And that's our task, to
Now,
give you a comprehensive professional overview of this mHC architecture and really detail how it fixes the scaling problems that were inherent in its predecessor, the unconstrained hyperconnections, or HC.
so to set the stage, let's just quickly revisit that bedrock, so the standard residual connection.
It's all about that identity mapping property. That's what ensures stability. When you think about the feature flow from, say, layer dollars all the way to layer dollar, that clean identity path guarantees the signal can propagate. It's a perfect stabilizer. It stops signals from just collapsing or, exploding.
And then came the ambition to break out of that simple mold.
Yeah,
Researchers saw this opportunity to, well, expand the residual stream itself.
precisely. And that's where hyperconnections, HEC, came in. They were a really key evolution. They expanded the stream width, going from a single channel C to nuller times C.
A huge jump.
A huge jump. And it added all this topological complexity, this potential for really rich feature mixing, but it did it without inflating the FLOP count.
And that was done by introducing this new learnable residual mapping, actual Marler, across all those new streams.
Right, but that's where the tension really comes in. You get all this new representational power, but you've just thrown away your safety net.
And that is the absolute core trade-off that mHC was designed to solve.
It is, because while HC showed these great performance gains in smaller tests, due to that rich mixing, it fundamentally broke the identity mapping property. You were trading stability for plasticity.
And at massive scale, that trade just ends in disaster.
Catastrophic instability.
Let's dive right into that fallout. The first of the two big challenges with HSC, this numerical instability. The paper points directly at that unconstrained learnable MHS mapping as the root of the problem.
It's the root cause. And it's not just a single layer that's the issue, it's the compounding effect when you stack them deeply.
So that's the recursion.
Exactly. When you recursively combine these mappings, you're really looking at this big composite matrix. It's the product of all the individual matrices across many layers.
And if those individual matrices don't follow some kind of conservation rule,
Then their product, that entire end-to-end residual path, it completely fails to preserve the global mean of the features. It just can't.
so we're not talking about a gentle drift. This is a fundamental structural flaw that lets the signal just become completely unbounded.
That's it. If that composite product isn't controlled, you get either unbounded signal amplification or, severe attenuation, the classic vanishing or exploding gradient problem. It just makes large-scale training impossible.
And the evidence for this is pretty stunning, especially when they pushed it to that 27 billion parameter scale.
Oh, absolutely. The 27B experiments were the nail in the coffin. The unconstrained HC model had this incredibly unstable loss behavior.
And they traced it back to something specific.
They did. A sudden, massive surge in the gradient norm at around the 12,000th training step. And to quantify it, they used this metric, the MX gain magnitude, on that composite path.
And the ideal value should be 1 for perfect stability.
1. The unconstrained HC model hit peaks of up to 3,000.
3,000. That is it's 3 orders of magnitude beyond stable. You're basically training a bomb to go off inside your network.
You really are. It's definitive proof that the residual streams are exploding. That kind of divergence means that, while HCC looks great on paper, in practice, you just can't train it robustly at scale.
Okay, that covers the theoretical breakdown. So let's shift gears to the practical side, the engineering challenge. The second big problem was system overhead, what the paper calls the memory wall.
Right. Each CISA was designed to be FLPI efficient, but efficiency, as you know, it's not just about FLOPs anymore.
It's all about memory access, I/O. That's the real bottleneck for GPU runtime now.
It is. And while HC kept FLOPs low, it introduced this massive I/O problem.
Right.
You've got knowledge streams of data, and you have to constantly shuffle features and mappings between all of them.
How bad was it, in tangible terms?
The analysis in the paper shows the per-token memory access cost scale is pretty much proportionally with that expansion rate, $1.
So more streams, more memory reads.
A lot more. The source breaks down the total I/O read cost to maintain those streams as $5 plus 1C plus N2 plus 2 and another elements. That's a huge increase in data movement for the actual computation you're performing, and it just kills your training throughput.
And then there are the secondary costs, which for any practitioner trying to scale these things are just as critical.
Absolutely. The intermediate activations you have to store for backpropagation, for all this GPU dollar mappings, they massively inflate the GPU memory footprint.
Which forces you into using things like gradient checkpointing.
Mandatory. You have to use aggressive checkpointing, which has its own compute cost. And on top of that, if you're using pipeline parallelism, that knowledge stream design means you have a null-fold higher communication cost between your pipeline stages. The whole thing just gets choked.
So enter mHC. The solution had to be, well, twofold. It had to be mathematical to solve the stability crisis and infrastructural to solve that memory wall.
Exactly. Let's start with the math. The core insight is to project that residual connection space onto a specific manifold.
Okay, so you're essentially putting a geometric guardrail on the learnable mapping.
That is the perfect way to put it. They realized the learning process itself needed a strict topological boundary, and the manifold they chose is key, the Birkhoff polytope.
All right, the Birkhoff polytope. For those of us who don't live in the world of convex geometry, what does that actually mean for the matrix?
It means two very simple things. First, all the entries in the matrix have to be non-negative. And second, and this is the crucial part, the sum of all the elements in every single row has to be 1, and the sum of all the elements in every single column also has to be 1.
A doubly stochastic matrix.
A doubly stochastic matrix. And this constraint forces the operation to be a kind of a feature averaging or a feature permutation across the streams. It guarantees mean conservation.
And the beautiful part is how this connects right back to the original stable ResNet idea.
That's the elegance of it. When your expansion rate in $none is just 1, so you're back to a single residual stream, this constraint collapses exactly into the original identity mapping. It's a generalized, but still stable expansion.
In choosing that specific constraint, the double stochasticity, it gives them these rigorous mathematical properties that directly address that instability problem.
It confers two vital guarantees. The first is what's called norm preservation. Basically, the spectral norm of that constrained matrix is bounded by 1.
So it's not expansive. It's the mathematical hard stop against gradient explosion.
It is. If the gain is bounded by 1 at every single step, the signal just cannot grow unboundedly. It puts a hard ceiling on how wild things can get.
That's the first property. What's the second one? The one that deals with depth.
That's compositional closure. The set of these doubly stochastic matrices is closed under matrix multiplication, which is fundamental for deep learning.
Meaning if you multiply them together,
they stay doubly stochastic. So when you multiply hundreds of these matrices together for the full composite path, that final matrix is still doubly stochastic. Stability is preserved no matter how deep you go.
That's the structural guarantee the original HC was missing. And the geometric interpretation you mentioned, a convex combination of permutations. What does that mean for how the features are actually flowing?
It's a really good description of what's happening. It means the output features are essentially a weighted, averaged blend of the input features. The mean is conserved because the weights always sum to 1. It's not some arbitrary, potentially exploding transformation anymore.
It's a robust, monotonic fusion mechanism?
Exactly.
So the math is fixed, but how do you actually implement this during training? Running an iterative optimization like Sinkhorn-Knopp on every single forward pass sounds expensive.
It's the critical implementation hurdle for sure. The process has two parts. First, they use a sigmoid function to enforce the non-negativity on the input and output mappings, re and not towed. That's pretty standard.
But the real heavy lifting is on training.
Right. That's where they use the Sinkhorn-Knopp algorithm. You start with your learned mapping, make the elements positive, and then you just iteratively rescale the rows to sum to 1, then the columns to sum to 1, and you repeat.
So Sinkhorn-Knopp is like a fast, real-time way to enforce that stability during training.
Yeah.
How many iterations did they actually need?
Well, mathematically, it only converges at infinity. But for practical purposes, the paper found that they got the stability they needed with just a small, fixed number of iterations. Specifically, Tmax equals 20.
Okay, so that trade-off makes it feasible.
It does.
All right, stability is handled. But like we said, that's not enough. You need efficiency. The authors were promising only a 6.7% training overhead with an expansion rate of 4. That must have required some serious engineering.
It absolutely did. It was a full stack optimization right from the GPU kernel level. They used tools like Liang to streamline everything and then leaned very heavily on aggressive kernel fusion.
Fusing operations to minimize I/O.
Yes, minimizing reads and writes. Reordering operations, like running RMS norm after the matrix multiplication to consolidate memory access using mixed precision. The whole playbook.
Let's talk about the biggest I/O gains. They developed a couple of specialized kernels, right?
They did. The first was a unified kernel to fuse 2 scans on the hidden state, $6, which is great for memory bandwidth. But the second one was the real knockout blow to the memory wall.
And that was?
The kernel that fuses the application of no-hole post store with the final residual merging. They call it the 5-post kernel.
So what was the I/O reduction from that one fusion?
It was dramatic. They cut the number of elements read from memory from $3 plus 1C day down to just O plus 1C.
Wow.
And writes dropped from $3,000 down to F-filers.
Wow.
That single operation cut the I/O demand by more than half. That's the secret sauce behind that tiny 6.7% overhead.
That's a huge reduction. But beyond fusion, they also used a strategic recomputing technique to deal with the remaining memory footprint.
Right. They realized that storing all the intermediate activations for the mHC kernels was still too costly, so they just discard them after the forward pass.
And recompute them on the way back.
Exactly. Recompute them during the backward pass, but they exclude the really heavy-duty layer function math call.
But you can't just recompute everything, right? You have to manage that carefully.
No, you have to be smart. They determine an optimal block size for recomputing, law of dollars, by minimizing the total memory footprint. And in practice, this usually gets synchronized with your pipeline stage boundaries. It's a very elegant solution.
Here, finally, communication overlapping. That's crucial for pipeline parallelism. And HEC's end-stream design adds latency. How did they stop that from blocking the compute?
They extended an established scheduling approach called dual pipe. The key move was to assign those computationally intensive 5-post kernels we just talked about to their own dedicated high-priority compute stream.
Why do that? Why dedicate a stream?
To decouple them from communication. By making those compute operations high priority and separate, they make sure that communication across the pipeline stages doesn't block the most frequent and complex compute steps. It guarantees high utilization, which is non-negotiable at this scale.
So that whole stack manifold constraints, kernel fusion, recomputing, and the dual pipe extension, that's what makes mHC truly scalable.
Which brings us to the results. Did it actually work? Did the constraints stabilize the network?
Unequivocally, yes. They reran the stability analysis.
Yeah.
And remember, the unconstrained HC peaked at an MX gain magnitude of 3,000.
Right.
For mHC, the maximum composite gain is bounded, peaking at about 1.6. And that's even with that practical limit of just 20 iterations for sync or knob.
So 1.6, it's a little non-expansive, but compared to 3,000, that's a massive 3-order of magnitude success.
And you can see it in the visualizations of the matrices themselves. The HC matrices had these wild positive and negative values, signs of impending doom. The MHC matrices are stable. The row and column sums stay right around 1. The future mean is conserved. So, onto the main goal. Performance. The results for the 27B models look pretty comprehensive.
They are. mHC consistently outperforms the baseline residual network, and it clearly surpasses the unconstrained HC architecture on most of the 8 downstream benchmarks they tested, things like MMLU, DRP, and BBH.
And the gain over HC specifically, that's the real proof point.
And that's where the stability really pays off in cognitive ability. mHC delivered a 2.1% performance gain on BBH and 2.3% on DRP compared to the original HC, and those are heavily reasoning-focused benchmarks.
Indicating that restoring that stable signal flow actually helps the network learn more complex reasoning.
That's the takeaway.
Okay, finally, true scalability. Did this advantage hold up as models got bigger and data budgets increased?
It did, and very robustly. The compute scaling curves across 3B, 9B, and 27B parameter models show the performance advantage of mHC holds steady. And the token scaling, training a 3B model on 1 trillion tokens, confirms it holds true across massive data scales, too. The optimizations worked.
So the core conclusion here seems pretty definitive. mHC successfully restored that essential identity mapping property using these geometric manifold constraints, and then backed it up with some really clever high-throughput kernel optimization.
And that combination is what enabled stable, scalable training while keeping the powerful representational benefits of that expanded architecture.
That's the summary.
But the framework itself, I think that's what should really excite you for future work. Yes, doubly stochastic matrices worked here, but the mHC framework is general. It's an invitation to explore all kinds of different manifold constraints to optimize that trade-off between plasticity and stability.
It pushes the whole conversation about macro architecture beyond just connecting layers and more into the actual geometry of feature flow.
Indeed. The question mHC poses isn't just if we can expand connections, it's how we can use geometric constraints in the topology to unlock new paths for optimization and learning. That interplay is where the next generation of architectural gains will be found.
So as you look at your next big scaling project, the provocative thought we'll leave you with is this. If the stability of an entire foundational model can be boiled down to enforcing some basic geometric constraints on feature flow, what other complex architectural problems like sparse gating or even attention dynamics might also be solvable just by projecting them onto a carefully chosen algebraic manifold?